Good afternoon. I'm Spot On Weather meteorologist Matthew Euler, and welcome to the How the Weather Works training series. This is part 12B, and we're going to finish up on the topic of thunderstorms. And in today's training, I'm going to be talking about a lot of exciting things when it comes to thunderstorms, ranging from the various thunderstorm features that we see, the formation of lightning, the types of lightning that exists, and much, much more. On the main slide here to start today's training, I'm showing a cloud-to-ground lightning strikes, multiple ones in this particular time exposure photo. Really neat stuff here. Very powerful, of course, lightning can be, and can definitely be some dangerous statistics involved with lightning as well. So let's go ahead and get into today's training. So we're going to start today's training off with a discussion on some of the specific features associated with thunderstorms. We're going to start first with a talk about gust fronts. Now these occur generally with both air mass and supercell thunderstorm types. The gust front acts similar to a cold front in that the wind shifts and becomes quite gusty, occasionally exceeding 55 knots. You'll see a temperature drop and a surface pressure rise as a gust front moves through the area. Now, what's happening with gust fronts? Near the ground or the surface, the cold, dense air extends outward from a thunderstorm, and it produces a shallow area of high pressure that is known as a meso-high. And along the leading edge of the gust front, the air is very turbulent. Again, this is that leading edge of the gust front. As it moves into the warm, moist air ahead of it, generally tends to lead to a lot of turbulent vertical mixing of the air. Now, with gust fronts and with other thunderstorm features, we also have special thunderstorm cloud types. So as that warm, moist air rises along the forward edge of the gust front itself, a cloud known as a shelf cloud forms. This is also known as an Arcus cloud. I'm going to have a picture of what these look like here in a minute, by the way. These clouds, these shelf clouds, are prevalent when the atmosphere is stable near the base of the thunderstorm, and you get an elongated, ominous-looking cloud that forms just behind the gust front. That type of cloud is also a special feature known as a roll cloud. That's right behind the gust front. And roll clouds appear to slowly spin about a horizontal axis. So let's take a look at some of these clouds visually now. All right. First thing I want to mention here when we look at these graphical visual images is I want to point out what's happening in relation to the thunderstorm, okay? Now, I want to start with the upper right-hand diagram here. It kind of explains what a gust front is all about, okay? So out ahead of a gust front, as the red arrows indicate, you have warm, moist air that's rising. Again, consider this gust front. This gust front is really another version of a cold front in the atmosphere. So you have these blue arrows in the diagram here, the upper right, that depict the cooler downdraft air coming out of the thunderstorm cloud. And associated with the colder downdraft, you typically get the heavier rain showers and the gusty winds. Right behind, on the leading edge of the thunderstorm, this boundary right here, this boundary is the gust front itself. So you can see how the gust front separates the colder downdraft air coming out of the thunderstorm and that warmer, moist air out ahead of it, okay? And then in the middle of the atmosphere, above the ground, you get this roll cloud, which is this horizontal rotating cloud. Here is what a roll cloud looks like, by the way. Notice how long in the horizontal this type of cloud is. This is a really great example of a roll cloud right here. Very stretched out horizontally. As you're sitting on the ground looking up at the sky, you may actually see this cloud rotating in the horizontal. Now, a shelf cloud, also known as an Arcus cloud. This is an example in the upper left of what that may look like. You notice the shape is a little bit different than the roll cloud. See how much longer and stretched out the roll cloud is in the horizontal? With the shelf cloud, you kind of see what's going on here. You got the colder downdraft air right here beneath the cloud. So you would expect a sharper temperature drop here beneath the cooler downdraft air as it reaches the surface with the heavy rain showers. So we have seen shelf clouds in quite a, it could be air mass thunderstorms, quite a high frequency of time we see shelf clouds with thunderstorms. All right, so we talk about shelf clouds, we talked about gust fronts. We also have to talk about special type of terminology associated with thunderstorms. And I'm going to cover outflow boundaries, downbursts, as well as microbursts. So when gust fronts tend to merge from multiple cell thunderstorms, an outflow boundary is generally formed. The converging outflow boundaries can actually help ignite new thunderstorm development. Okay? And I kind of hinted at this back in the How the Weather Works 12A training of how you can get multiple outflow boundaries moving towards each other and igniting new thunderstorms. Let me just draw it out here once more so you can kind of see what's going on. All right, so let's say that I have an outflow boundary. This red line represents one outflow boundary, and it's generally heading in this direction here, as indicated by the arrow. Let's just say this direction is towards the southeast. And then I have another cluster of storms over, there's another cluster of storms over in this direction here, okay? And the outflow, the colder downdraft air is producing an outflow boundary that is setting up like this. And let's just say that that outflow boundary is moving towards the other outflow boundary. Now, once these two outflow boundaries meet or merge, the air eventually is going to be forced up to rise in the vertical, and that could generate newer thunderstorms. So you really have to keep an eye on the outflow boundaries, where that cold downdraft air, how it's spreading out horizontally along the surface, and where these particular gust fronts or outflow boundaries, where they merge. Because, it could result in new development of showers and thunderstorms rather easily. And I'm going to show you some examples of what these outflow boundaries look like on various weather tools here shortly. Okay, so let's move on now with the training. Go ahead and erase that, get that out of the way. All right, so now we're going to talk about beneath intense thunderstorms, a downdraft is generally going to hit the ground. It spreads out horizontally in this radial burst of wind, and this is known as a downburst. So now let me draw out what a downburst looks like. Okay, so let's just say that this right here is the base of your thunderstorm. I'm going to make a big thunderstorm cloud with a nice big anvil. There it is. Okay, a big tall cumulonimbus cloud. I'm going to have colder air that is going to come out of the cloud, all right, down from the cloud itself. This cooler downdraft air comes out of the cloud, and then here is my surface right here. And when that cooler downdraft air hits the surface, it's going to spread out horizontally. Okay, it can't go down into the ground, so it spreads out horizontally like this. And that is known as a downburst. When you get very cool downdraft air hitting the ground, spreading out radially outward from the surface in all directions, this is known as that downburst. Okay, downbursts can be very deadly. Okay, so I want you to think about this. Let me go ahead and erase this. I'm going to draw you one other picture. Downbursts can be very, very deadly to aviation, to the aviation community, to pilots in particular. Because what happens is, all right, let's say that this is the surface here. Okay, that's a surface. And of course I have my thunderstorm cloud again up here. Here's the base of the thunderstorm cloud. There's my tall cumulonimbus cloud with an anvil. Okay. Now, let's say I have an airplane, all right, that is right here. Okay. Please forgive me for my drawings. I'm not a artist by any stretch. But anyway, so let's say this is your airplane here, over here on the left, right here. Okay. And it is now descending, trying to land at this particular airport. So if this is the ground down here at the bottom, it's on its descent, its final descent. to land at a specific airfield or airport runway, and I've got these very strong downburst winds coming out of this thunderstorm cloud right over the airport. So as this plane descends, once it gets beneath these downburst winds, what's going to happen is those downburst winds are going to result in that airplane suddenly losing control as it comes down to land, because these downburst winds out of the thunderstorm are going to push it into the ground. And that has resulted in many disasters. I'm thinking of Dallas-Fort Worth Airport. There was an airline that came in there, very strong downburst winds. In fact, Dr. Ted Fujita, Mr. Tornado, actually studied this. He was actually hired to look into these downburst effects from thunderstorms. What they ended up doing at the airports is developing these low-level wind shear alert systems because of these deadly crashes that some of these airlines were having upon when they were descending to land at airports, because these downburst winds were pushing these planes into the ground, and unfortunately there were a lot of fatalities involved. And so now we have what's known as low-level wind shear alert systems around major airports. So even with thunderstorms in the area, we can keep track of what's going on with the airflow out of these thunderstorms and keep pilots much more safe. But just wanted to show you how deadly these downbursts can be, especially with pilots. And we've had some incidents before in the past. If you just Google it, you're going to find a lot of downburst aviation incidents, and you'll be able to really see that. All right, so now let me go ahead and erase this, and I just wanted to kind of show you schematically what that could look like and how treacherous a downburst could be to aviation. All right, now we're going to move into the size. Okay. Now, the size really does matter here, this third bullet. A downburst with winds extending only 4 kilometers or less is generally known as a microburst. So micro, M-I-C-R-O, I want you to think a smaller scale. A downburst with winds extending more than those 4 kilometers, that's known as a macroburst. Macro, M-A-C-R-O, being much larger area. Okay, so there's two types of downbursts. There's a microburst, where the air spreads out 4 kilometers or less, and there's a macroburst, which is a much larger scale downburst that extends more than 4 kilometers outward. Now, these intense microbursts are extremely dangerous to the aviation industry, as I already illustrated graphically, and have resulted in plane crashes. Not only the example I gave you of an airplane coming in to land on a runway, but also for takeoff purposes. Because as the airplane's trying to climb and ascend after it leaves a runway, if you get a downburst wind, it's going to basically push that aircraft back to the ground, and it could have disastrous consequences. All right, so now let's take a look at some of these products to kind of show you some examples. The first graphic here on the left shows outflow boundaries that are showing up on a radar depiction. Now, this is out of central Oklahoma. This was back in June of 1997. This is a reflectivity composite. So we're looking at the intensity in decibels of these returns. But I want you to pay attention to, there's a couple thunderstorm cores here in this example. Let me go ahead and get my pen out so I can point them out to you. Okay, so we have one thunderstorm core right here that's weakening. We have another thunderstorm core up here in the far upper left-hand portion of this graphic. That thunderstorm core is weakening, okay? So your decibel levels are getting less and less over time. This storm is weakening, but as it weakens, it's sending out those downburst or those downdraft winds, those cooler downdraft winds, out of the base of the thunderstorm. As soon as that downdraft wind hits the surface, it spreads out horizontally, and you can actually see on these reflectivity products, this is an example of an outflow boundary right here. And then here's another example outflow boundary with this weakening cluster of thunderstorms. Okay? So it's important to pay attention, and if you put this in motion, this particular radar image, you animate it, you can actually see the motion of these outflow boundaries. So, it's important to pay attention to where the outflow boundaries are going. On this particular day, the outflow boundary was spreading to the northeast with this particular cell, the dying thunderstorm core up here, and it was spreading to the northwest from this core at the bottom right-hand portion of the graphic. So there's a good chance that these two outflow boundaries will not merge. in the development of new thunderstorms in this case. But you have to pay attention to that stuff, okay? That's why I'm mentioning that, these outflow boundaries, and where they meet or converge. Here's an additional example. This is a downburst. This arrow kind of tells you what's going on with the thunderstorm. Notice this big, thick green arrow just showing the general downward motion of this cooler downdraft of air coming out of the thunderstorm cloud. And then once this downburst or downdraft hits the ground, it's spreading out now more horizontally as it hits the surface. You're noticing that? And you also can note where you see this rain shaft. You notice how this darker gray area is and how it goes all the way to the ground in this portion of the thunderstorm. That to me tells me this is the downburst or the downdraft area of the thunderstorm, because as the cooler air is descending out of the clouds, it's dragging all the rain droplets with it, and you usually get the heavy rain showers with the downburst winds or the downdraft winds. And by the way, it'll feel much cooler outside. Before this reaches you, the downdraft, you may be sitting at, let's say, 86 degrees Fahrenheit, and after the downdraft winds come down out of the base of the thunderstorm, your temperature may drop 10 to 15 degrees over a very short time period. And also, another neat thing to look at when I look at this particular graphic showing the downburst with the heavy rain showers, I also note this is most likely an updraft portion of the storm. See how there's no rain shafts here? It's very light colored background. That to me tells me this is most likely an updraft area. So you got warm, moist air ahead of the edge of the thunderstorm. That warm, moist air is being fed into the thunderstorm circulation on the right-hand side of this graphic here. Okay. And here's an example, finally, at the bottom here, of the slide, showing you, just again, delineating the differences between a microburst and a macroburst, okay? Micro being a much smaller area. Here's the definition in miles. I gave you the definition earlier between a micro and a macroburst in the kilometer units, 4 kilometers. Here it is in miles, a microburst, damage expanding 2.5 miles or less, whereas a macroburst, damage expanding greater than 2.5 miles. And look at this rain shaft here. Wow, this is a really good depiction of a downburst. Note how I can just draw the circulation pattern with these arrows based on this visual depiction of the thunderstorm. Generally, you see the heavy rain shafts going all the way to the ground here. This is where the thunderstorm is collapsing. This is where you're getting your heavier rain showers, gusty winds. And these winds can be very damaging too, by the way. These straight line winds is what they're known as, and they can cause just as much damage as a tornado. In fact, the National Weather Service will send teams out after damaging thunderstorm events. They send teams out to the field to determine whether it was a tornado that caused the damage or just general straight line winds. But this is a really neat picture here showing downdraft air coming down out of the base of this thunderstorm, very heavy rain showers in this area, and then look at how the circulation, how the air spreads out horizontally. Once the downdraft hits the ground, it's got to spread out horizontally at this point. And it can result in either a macroburst, distance dependent, or a microburst, okay, smaller area, again, distance dependent. All right, so now let's move into a topic on a very interesting phenomenon when we talk about thunderstorms in general in summertime, derechos. And then we'll also delve into the topic of what's known as a bow echo. Now, the strong downburst winds associated with a cluster of severe thunderstorms, they can produce those damaging straight line winds, just like I mentioned on this slide here when we were talking about it. Damaging straight line winds, as I mentioned, I'm kind of getting ahead of myself, they can cause extensive damage similar to a tornado and with a damage swath wider than 240 miles. Now, if the wind exceeds 90 knots and the damage extends for several hundred kilometers along the storm's path, the winds are called a derecho. Now, a derecho forms in the early evening and lasts throughout the night. Most derechos form, climatologically speaking, in the months of May, June, and July. And often, thunderstorms on Doppler radar appear in the shape of a bow. All right, that is known as a bow echo. That's the second part here of what I'm going to talk about. Okay, so the first point, first three bullets, we're talking about derechos. Okay, we're talking about derechos, very great amounts of damage swaths, wide swaths of damage, wider than 240 miles. There was a very dangerous derecho that formed last year in the state of Iowa, which just completely destroyed cornfields. Just crazy the damage after this derecho came through. Winds were over 70 miles per hour with it. So in general, the first three bullets refer to derechos, and we'll talk a little bit about that in a minute. And then the last bullet here, when you're looking at a Doppler radar product and the thunderstorm line appears in the shape of a bow, this is known as a bow echo. And bow echoes typically are associated with what's known as squall lines. So let's take a look here. All right, graphically, let's take a look at some of these features. Okay. The first one we're going to take a look at is the upper left-hand image here. This happened to be a very damaging derecho event which occurred. This one might have been the 2012 derecho. I don't have the date in front of me right now, but in general, we have these time frames denoted in the blue boxes. Okay, so we start at 7 a.m. Eastern time with the position of the derecho. Let me get my drawing tool out. The derecho starts off right in this area at 7 a.m. Eastern Daylight Time on this specific day. And you'll notice, too, how the derecho, it covers an area 500 miles long. Okay. By 9 a.m., the derecho is at this location into northwestern Pennsylvania. Between 9 and 11 a.m., it's now into central Pennsylvania. By 11 a.m., it's all the way moving towards southeastern Pennsylvania. By 1 p.m., it's there in southeastern Pennsylvania. And then by 3 p.m., this derecho is already offshore into the western Atlantic. So these derechos tend to move in northwesterly wind flow. Usually have fairly strong northwesterly wind flow, which pushes these type of phenomena along at a very quick rate, and they are associated with damaging straight line winds. Okay, and this is a great example of a reflectivity product. By the way, when you see the red coloring on the reflectivity product for Doppler radar, that is the strongest. These are the strongest cells within the derecho itself. Now, I mentioned to you about the Iowa derecho, and this is what the damage was after the derecho. Winds in excess of 70 miles per hour. I believe it was last summer. Look at the damage. Look how flat these cornfields are from those damaging winds coming down out of the derecho. I mean, it's leveled. This is damage. It's terrible damage. These are terrible losses for the farmers. If you look at the connection there between these two, it's very deadly. Now, on the upper right-hand portion, I'm showing you an example of, this is a squall line, more specifically a bow echo. Let me go ahead and, okay, so initially we have points A through D listed here. This is a bow echo example. We're developing a squall line. Notice how initially the shape of the thunderstorm is mostly symmetrical, right? Not much bending of this radar reflectivity. By the way, the red is the most significant decibel reflectivity, by the way. The lighter green is the weakest reflectivity or weakest returns. So as we get towards B, we're starting to see these dark arrows in the center here behind this developing squall line. This is your rear inflow jet, RIJ, and notice how you're getting a counterclockwise circulation at the northern end of this bow echo, and you're getting a clockwise circulation on the southern end of it. So now we're starting to get stronger push of winds in the center of this particular line of storms, and eventually what's going to happen is this push is greatest right here where the radar echoes bow out. Okay, this is where you're going to have your greatest potential for damaging winds. Whenever you have the bowing feature, this bow echo, on the squall line, that's where you're going to be worried about the most significant wind damage. Right? And over time, what happens is it continues to bow out the line of storms, and again, this is your bow echo right at this point here. Here is an example of the various pieces or parts of a bow echo. On the ends, when we talked about these two areas, the north end, the counterclockwise circulation. On the south end of the line, we have a clockwise circulation. Those are what's known as bookend vortices. So you got vorticity or spinning of the air at the ends of this particular bow echo. Additionally, you have a rear inflow notch, the rear inflow jet, generally right at the point where the rear inflow jet has the strongest wind speeds and is tended to push this portion of the line of storms out, the bow echo out much further. You have downbursts out ahead of the particular bow echo. You have an apex, which is the point at which the echo bends out to the greatest level. And this is what it looks like on radar. This is a reflectivity product. This is an example of a bow echo. Now, judging on this particular reflectivity product, guess what? Guess where I'm going to have my greatest wind potential, wind damage potential? It's going to be located generally right in this location here, because this is the point at which that bow echo bows out the greatest. We got a rear inflow notch here, or a rear inflow jet, and you'll notice you have some weaker reflectivity associated with that rear inflow jet, okay, or the rear inflow notch. So generally, these are very interesting features when we talk about thunderstorms. Derechos, a very intense system. It generally moves in northwesterly wind flow, and it moves very quickly, can result in a very large swath of damage, wind damage, can flatten cornfields like this in the bottom left, and then bow echoes. As a rear inflow jet pushes the line of thunderstorms out in this particular shape, that's known as a bow echo. All right, so now let's move on to a special type of system associated with thunderstorms. This is known as a Mesoscale Convective System, or MCS. And all this is a large complex of thunderstorms that have an extensive size and persist for several hours or more. Now, they may be round in shape, such as a Mesoscale Convective Complex, or MCC, or they could be linear in shape in the form of squall lines. So when we talk about MCS, the system, it can be composed of MCCs, round Mesoscale Convective Complexes, or linear line of thunderstorms known as squall lines. And mesoscale convective systems can also include tropical cyclones, believe it or not. They often form in west to northwest flow aloft, and they travel hundreds of miles, and they can last as long as 18 hours. So this is not your normal thunderstorm on a summer afternoon. So let's talk about squall lines. A squall line generally forms as a line of thunderstorms, typically along or ahead of approaching cold fronts at the surface. And when I say along or ahead, I'm talking 100 to 300 kilometers ahead of an approaching cold front. You're in the warm sector of a cyclone. Squall lines tend to pass rather quickly, hundreds of miles long. They're only about 10 to 20 miles wide on average, though. So they're longer than they are wide. They typically occur east of the Rocky Mountains, especially in spring when the atmosphere is most dynamic. A bowing line segment, which we already just talked about, is known as a bow echo, the bowing line segment of a squall line. The apex of the bow has the strongest winds, or the greatest potential for that straight line wind damage. And tornadoes tend to be short-lived and weaker as compared to supercells. So you can get thunderstorms or tornadoes with these squall line features. Let me show you what one generally looks like. Now, I've lived on the Gulf Coast, and these happen quite frequently down there on the Gulf Coast. That's where I've experienced them the most, in the Florida Panhandle. And generally, a squall line is going to form basically like this, just this nice long line of thunderstorms. And typically, here's an area of low pressure, okay? And then you got a warm front extending from eastward from the low pressure, and then you have a cold front extending southwest ahead of or behind the squall line itself. So you got warm, moist flow of air from the south ahead of the cold front. The air is cooler back here behind the cold front, behind the area of low pressure, and you got southerly flow ahead of the cold front. You're in the warm sector of the cyclone, and that's generally where you're going to get your squall lines to develop, out ahead of surface cold fronts. Mesoscale convective complexes, on the other hand, I've lived in the Midwest before. I've seen these things develop, and these things are prolific rain producers. These complexes can produce Very heavy rain over short periods of time. Very persistent. Can last in the order of up to 12 hours. And one other interesting thing about mesoscale convective complexes is they can form at nighttime and they last. Like I said, they are long duration events. This is where individual thunderstorms, they grow in size, they organize into these larger convective weather systems. Again, prolific flood producers, very heavy rain showers. Usually you'll see the National Weather Service issue either a flash flood watch. A lot of cases it happens in real time to where the Weather Service will just jump right to a flash flood warning. They form at night, and I've experienced this at night back in the Midwest where this huge cluster of thunderstorms just forms and it just dumps rain. There's lightning and thunder associated with these. They last for just long periods of times. And the main reason is because the upper level winds are so weak, in the summertime, there's really no strong push to get these things out of an area. They tend to stagnate or move very slowly out of an area. That's why you get such heavy rain showers with these things. They're often large enough to cover an entire state. I've seen a convective complex, a mesoscale convective complex. I've seen one of these cover the entire state of Iowa. In excess of 100,000 square kilometers is the total coverage they can cover. It's amazing to see it. Within the MCC, individual thunderstorms work together to generate a long-lasting weather system. And I already hit this point. They move very slowly, and that's why you get such prolific rainfall. They're slow movers, usually move on the order of less than 20 knots. They are responsible, MCCs, for producing hail. Hail can be associated with these, definitely damaging high wind gusts, destructive flash floods. Now, in some cases, you can get tornadoes out of these things, out of these clusters, but a lot of times I don't see many tornadoes out of the MCCs. A lot of times the main features are the high winds, dangerous lightning, and destructive flash flooding, extremely heavy rain showers. Tornadoes are possible with any thunderstorm. You just have to look at that, but you're really lacking the wind shear necessary for tornadoes with MCCs. The upper level winds are generally weaker, so you're not getting a lot of turning of the wind with height. So again, this is very seldom when it comes to MCCs and producing tornadoes. They generally form during the summer in the regions where the upper level winds are weak, often beneath a ridge of high pressure. And if you get a weak cold front that stalls beneath the ridge, surface heating during the day and that excessive moisture where the air is really muggy, you have high humidity, that may be sufficient enough to generate thunderstorms on the cool side of the frontal boundary, and that moisture is brought into the system from the south by a strong low-level jet stream. It's all the ingredients, folks, for a mesoscale convective complex to form. Now, MCCs, they tend to reach max intensity in the early morning hours as the low-level jet reaches maximum strength overnight. So guess what? We're not talking about needing the sun out with this type of thunderstorm complex. Most thunderstorms form during the heating of the day due to the instability produced by the sun being out. MCCs do not rely on that at all. Cloud tops generally cool at night, and what that does is when the cloud tops cool at night, they rapidly emit infrared energy to space, and the atmosphere now becomes more unstable as latent heat is released in the lower and middle parts of the cloud. And due to weak upper-level winds, most mesoscale convective complexes, or MCCs, move eastward very slowly. Now, I like to really take a look at this second bullet. This is interesting to me, okay? So let's go ahead and draw out what's happening, okay? So let's just say this is the surface, and here's your MCC cluster, okay? And I'm just going to draw out a, let's just say this is a group of thunderstorms here, okay? There's my anvil again. I know I'm not an artist, everybody. This actually looks like a slice of bread, doesn't it? I apologize. All right, so anyway, the upper portions of the cloud. First of all, let me just draw where theoretically we would see a freezing level at 0 degrees Celsius. So let's just draw this horizontal line straight across. Hopefully I can get that done here. Yeah, here we go. So let's say that this is the freezing point. This is the 0 Celsius. This is 0 degrees Celsius. Boy, I look like a kindergartner drawing this out. All right, but anyway, this is the freezing line. Anything above this line is below freezing. It's ice. So you got a lot of ice in the upper portion of this cloud. Okay? And what also at nighttime, what we have, think about this, If the cloud tops cool at night rapidly, they emit higher energy to space. So you have cooler cloud tops. All right. When you emit more energy, higher energy out to space, okay, you're cooling at cloud tops. Meanwhile, in the lower and middle portions of this cloud, latent heat is being released as you convert water vapor to a liquid, the condensation process. You are releasing latent heat to the surrounding air in the lower and middle parts of the clouds. So what you're doing is you're creating a greater temperature contrast in the vertical. Oh boy, that A was rough. Okay, you got warm air at the bottom of the cloud. You got cooling air aloft. Cooling cloud tops up here and warming temperatures in the lower and middle portion of the cloud. So cold over warm, and I talked about this in my last video, the COW, C-O-W. When you have colder over warm, that is unstable. And this is what keeps this thing alive at nighttime. It's a dynamic system. You have cooling cloud tops. So your temperature contrast between the lower and middle parts of the cloud being warmer and the cooler areas at the top of the cloud, it's becoming greater, it's becoming larger. And that is then going to result in stronger vertical air currents or convective currents of air, which is going to keep this thing alive for long durations of time. Hopefully that made sense to everybody. I just really I thought this bullet right here was really interesting, bullet 2. And I wanted to kind of depict that and show you what that looked like. Here is an example. This is an IR satellite image. This is showing you, these are temperatures, by the way, the different color scheme on this. So anything with this white and the purple and right in this area of the graphic on the left, that is the coldest cloud top temperatures. As we get outward away towards the edges of this mesoscale convective complex, we're seeing green and light blue. Those are your warmer temperatures associated with the clouds. Okay, so you can see, now I'm trying to think here. Okay, so this is Kansas. This mesoscale convective complex formed over Kansas. This is central and western Kansas. It almost covers the entire state of Kansas, by the way. It's that large. And notice the circular shape. See how it's more symmetric here? This is very typical of a mesoscale convective complex. Why? Because there's no upper level, the winds are very weak in the upper levels of the atmosphere. When you get here, let me draw this out. So whenever you have a circular cluster of thunderstorms, that tells me one main thing right away. That tells me that I have weak upper level winds. Okay? Because if my upper level winds were strong, my cluster of thunderstorms would be more asymmetric, like this. So let's just say I have strong southwesterly winds in this case. All right. My thunderstorm cluster on satellite is going to look much more asymmetric. Not symmetrical, not circular, but asymmetric. Okay. So I look at this and I say, okay, the upper level winds, mid-level winds are weak. They're light. They're not distorting the shape of this MCC very much. Now let's take a look at the radar return of a typical MCC. By the way, these two graphical images do not correlate to each other. This is an example of an enhanced IR satellite image on the left over Kansas showing an MCC. Notice the circular shape. Notice how large it is. Notice how these cloud tops are very cool in the purple and the white coloring. This image on the right shows a radar reflectivity product in decibels, showing you the oranges are the heaviest rainfall. The yellows are moderate rainfall. The greens are lighter rainfall. And this, by the way, is over Memphis, Tennessee. This is over eastern Arkansas, western Tennessee, and northern Mississippi. But you're getting the point here. See the circular shape again on the radar reflectivity with an MCC? And this thing is not moving very fast. And this could easily result in flash flooding over short time periods. And so you have to be very mindful of that. So, for example, if you're camping and you're paying attention to the weather app on your phone, if I'm camping, I see this kind of structure, I'm thinking to myself, okay, we have to start thinking of a plan, especially if you're in an area, campground with elevated terrain. I'm looking at this graphic, this satellite image on the left of MCC, and I'm thinking to myself, I need to get to higher ground immediately because this could be a potential life-threatening situation with flooding right away. I can look at this and tell you that. So now let's move and turn the attention from MCCs over to thunderstorm climatology. Where do thunderstorms generally tend to form the most throughout the course of a year in the United States? Okay. Well, the winner on thunderstorm days generally tends to be Florida. If you look at southwestern Florida, west of Lake Okeechobee, they average over 100 thunderstorm days per year. And what exactly is a thunderstorm day? It's a day at which thunder is heard. Okay. And then as you go westward along Interstate 10, the Florida Panhandle, you still are in that 80 plus thunderstorm day category, so very high frequency of thunderstorms, all the way into cities such as Fort Walton Beach, Destin, Florida, Pensacola, over towards Mobile Bay. And then that climatology high thunderstorm area extends from Jacksonville, Florida, up through South Georgia, South Alabama, all the way over towards Biloxi, Gulfport, Bay St. Louis, Mississippi, right to the edge of New Orleans. And then you have 60 thunderstorm days per year, extending further west in southern Louisiana along the Gulf Coast. And then the yellow generally indicates 50 thunderstorm days each year. Green is between 40 and 50. And then, of course, look at out here out the west coast. 5 thunderstorm days a year along northern California coast. 10 up towards Seattle and Portland. Look at Alaska, very low numbers. 5 to 20. And then Hawaii is even out here, the Hawaiian Islands, ranging from 6 to 10 thunderstorm days a year. So let's talk about some of the reasoning here, okay? Look at the west coast here. Why do you suppose that we have such low thunderstorms days along the U.S. west coast? It's very simple. We have a colder ocean current. We're on the stable side of the Eastern Pacific anticyclone or high pressure system. So we have very stable air masses typically right along the coast of the U.S., western U.S., okay? You also have a colder ocean current that tends to follow these general northerly winds on the east side of the anticyclone over the Pacific. So you get very stable air masses over the U.S. west coast. That's why you have such low numbers. Southern plains, southern U.S., Gulf Coast. This is an area mainly dominated by maritime tropical air, especially the Gulf Coast, where you're going to get, on the back side, the unstable side of the Bermuda High, you're going to get more moist maritime tropical air, very muggy, very humid, moving out of the Gulf of Mexico. And that more moist air tends to always want to rise in the vertical, and you typically get a lot more thunderstorm development on this part of the country. And then you notice a lower number up here towards New England, too. Well, why do you think that is? Again, it comes down to the airflow and the air masses. You get a lot of maritime polar air that tends to visit our friends up in New England, and that's more stable as well. So thunderstorms, in general, here's some facts about thunderstorms. They tend to move in the direction of the winds in the middle troposphere. That tends to be their steering currents. Supercell thunderstorms, very special type of thunderstorm. I talked a little bit about that in How the Weather Works training series, that video 12A, the one before this one. If supercell thunderstorms, when they become what's known as right movers, they generally move 30 degrees to the right of that mean or average wind in the middle troposphere, and at the speed of about 75% of the mean wind velocity. So with a supercell thunderstorm, sometimes you get a splitting effect where one supercell will be a left mover in comparison to the winds, and one of the supercells will become a right mover, where it breaks off like this. Now I want you to imagine that this is your mean wind direction right here, the middle arrow. This is your left mover supercell. This is your right mover supercell. And typically, you get more of a cyclonic vorticity or spin with the right moving supercell. So this is the one you have to watch closely for tornadoes, by the way. Just want to throw that out there. And when thunderstorms move over the same location repeatedly, that's a very dangerous situation in which you get very heavy rain and flash flooding. That's known as training, a training effect. That potential flash flooding, storms can also remain nearly stationary with those MCCs we talked about earlier if the winds aloft are weak. All right, now let's move on to the topic of lightning. Ooh, what an exciting topic this is. What is lightning? Simply put, it's a discharge of electricity which occurs in mature thunderstorms. The lightning may take place within the cloud, so intra-cloud lightning is possible. From one cloud to another, from a cloud to the surrounding air, that's cloud-to-air lightning, or from a cloud to the ground, that's that CG lightning strike. The majority of lightning strikes occur within the cloud, with only 20% of lightning strikes occurring between the cloud and the ground itself. And this is one heck of an interesting fact. Lightning stroke can heat the air to a level 5 times hotter than the surface of the sun. The surface of the sun is generally around 11,000 degrees Fahrenheit. Lightning strike or a channel of lightning can be up to 54,000 degrees Fahrenheit. The extreme heating within an air channel is going to cause the air to expand rather vigorously. This initiates a shock wave that we hear known as thunder, and that sound is going to travel outward in all directions from the flash. Light travels very quickly in general, but the sound of thunder takes much longer to reach our ears. You'll see a flash of lightning, then you hear that clap of thunder or that low rumble of thunder. You'll notice you see the flash of lightning first, right? Because that light is traveling faster than the speed of sound can reach our ear. We can determine how far away actually the lightning strike is by using the 5 seconds for every 1 mile rule. So here's an example. Let's say it's a hot summer day, you see a flash of lightning in the sky, and then you hear the thunder about 15 seconds after you see the lightning. We can use the 5 second for every mile rule to determine that that lightning strike was approximately 3 miles away from us. Now, I'm sure you've been in thunderstorms before where you see this vigorous flash of lightning and then it's almost instantaneous where you hear a clap of thunder. That is a case where that lightning was much closer to us. And you definitely don't want to be outside when lightning's happening because the risks are very great to be struck by lightning. Okay, so great example here. For every 5 seconds after you hear, so basically you see a lightning flash. For every 5 seconds after is 1 mile is the distance from that lightning strike. So let's say now that we see lightning and then we hear thunder 5 seconds later. That would mean that that lightning was about 1 mile from our location. Here is lightning climatology, generally showing red and white colors indicate the greatest frequency of lightning. Now the cool thing about this particular map is I'm showing the whole entire world. So if you notice, where does lightning occur the most? It occurs generally over heated land masses, of course. You don't see it as much over the ocean. I've been out to sea many times on ships, and even around developing tropical cyclones, it's very rare to see flashes of lightning over the ocean. I've never seen it, actually. But in general, you can see here along the equatorial areas where you have very strong sun angle, the air is very warm and moist year-round. You see a lot of orange shading down here on the equator. You also see a lot of lightning frequency, higher frequencies over eastern United States. You're on the unstable side of the Bermuda High with warm, moist maritime tropical air mass during the summertime, east of the Rocky Mountains. Over Europe as well, Central Europe, and then also the Western Pacific Ocean in parts of China, Vietnam, Laos, Cambodia, the Philippines, some of Southeastern Asia here. You see a lot of lightning too. Now, how does lightning form? This comes down to one simple fact, and that's the electrification in the clouds. So within a thunderstorm cloud itself, what happens is you get separation of positive and negative charges. The negative charges are typically located in the lower portion of the thunderstorm cloud, and those are associated with water droplets. Now you get above that freezing level, in the higher reaches of this very tall vertical cloud, you're going to have positive charges at the top of the cloud. And these are associated with these ice crystals. So once you get these updrafts and downdrafts, I'm going to draw this out. This is a really good example here. So here's here's the ground. Okay, here's the thunderstorm cloud again. I'm going to draw a nice big anvil. Okay, all right. So let's say that this horizontal line represents your freezing level, 0 Celsius. Anything above this horizontal line in the middle of this particular graphic is going to be below freezing. And so everywhere above that freezing line is going to be ice crystals, okay? I'm drawing these little stars, these little asterisks, they represent my ice crystals in the upper portion of the cloud, okay? Anything below the freezing level is going to be more liquid drops. So I'll just draw like these solid vertical lines. This is my liquid drops, okay? Now, what happens within a thunderstorm? You're going to get one side of the cloud during the mature stage, which is going to have your updrafts, and then you're going to have, on the mature stage, the other side of the cloud is going to have downdrafts. But what happens here is as these liquid water droplets are carried on the vertical air current, the convective current, into the colder portions of the cloud, what happens is you're getting a mixing of ice crystals and liquid water. And there's charges associated with each of these. So you have negative charges at the bottom of the cloud associated with water droplets, and then you have positive electrical charges associated in the upper portion of the cloud with these ice crystals. And you get these up and down currents just moving the liquid water droplets up into the cloud, higher up into the cloud. You have the downdraft bringing the ice crystals down to the lower portion of the cloud, and you're going to have contact between the ice crystals and the liquid water droplets, and that's going to result in electrical changes within the cloud itself. We call it electrostatic potential. Eventually, the difference in the electrostatic potential, or the difference in electrification or charges, is going to be so great, it's going to overcome the poor insulating effects of the air, and you're going to be having an electrical current flow and lightning to occur. Here is another example of it, kind of what I just drew. So you notice here, if this was the freezing line here in this diagram, anything above this red horizontal line is below freezing in the upper portions of the cloud. Now, thunderstorm clouds can grow up to 50 to 60 to 70,000 feet in height. So you're covering quite a range of temperatures in the atmosphere. Okay, so you got a lot of liquid water droplets here at the base of the thunderstorm cloud. You got positively charged ice crystals in the upper portion of the cloud. And then below the cloud, so below the cloud, with the negative water droplet charges in the bottom of the thunderstorm cloud, but below the cloud on the surface, you actually have positive charges again. So we have, and I'm just going to draw it over here on the side, you have a positive charge in the upper portion of the cloud, a negative charge within the bottom portion of the cloud, and then within the shadow of the thunderstorm cloud itself, you end up getting a positive charge on the ground again. So see the differences here? Opposites attract, right? See that? Positive, negative, negative, positive. And so eventually over time, the electrostatic potential between the positive charges and negative charges becomes too great. Positive and negative, it becomes too great. And again, air is a poor insulator. Eventually, the charge becomes so great that you get this lightning bolt to come down. Ooh, look at that. From the positive to the negative areas, the charged areas. So cloud-to-ground lightning. Now, when you look at cloud-to-ground lightning, this is something interesting. We talk about this particular type of lightning. It looks to the human eye as if the lightning strike is occurring from the cloud down to the ground, right? Not necessarily the case. Our eyes are very much deceiving us. I'll talk more about a step leader here in a minute. Some of the facts here about cloud-to-ground lightning first, before I get ahead of myself. Cloud-to-ground lightning begins within the cloud when the localized electric potential gradient it exceeds 3 million volts per meter along a path around 50 meters long. So now I'm breaking down the exact electrostatic potential necessary for cloud-to-ground lightning. A discharge of electrons occurs toward the cloud base and toward the ground in a series of steps, and each discharge covers about 5,100 meters, then stops for about 50 millionths of a second, then occurs again over another 50 meters. This results in a phenomenon known as a stepped leader, and it's usually faint and invisible to our naked human eye. And as the stepped leader approaches the ground, the potential gradient voltage per meter increases, and a current of positive charge starts upward from the ground, usually along elevated objects to meet it. And after they meet, a large number of electrons flow to the ground, resulting in the more ominous return stroke. And even though the bright return stroke travels from the ground up to the cloud, it happens so quickly that our eyes cannot resolve the motion. So what I want to get at here is, as I was kind of alluding to, when we see cloud-to-ground lightning, like a lightning bolt come out of a cloud, we can't perceive the fact of what's happening here. Okay, let me draw this out. All right, so if this is the ground here, and this is your thunderstorm base, thunderstorm cloud base, here's your thunderstorm cloud up the top, okay? I mentioned that if this was your freezing level, you have positive charges up at the top of the cloud, right? You have negative charges below the freezing level with the water droplets in the lower portion of the cloud. And then you have this shadow of a positive charge. And let me just draw out something here. Let me just draw this out. Let's imagine that this is a tree. This is a tree right here. Okay. This is a tree. What's going to happen here in the shadow of the thunderstorm cloud is you're going to get positive charges that are going to move up tall objects, such as this tree. Guess what's going to happen? This electrostatic potential, or the electrical difference between the base of the cloud and these taller objects, which are now emanating positive charges upward towards the base of the cloud, eventually what happens is you end up getting a cloud-to-ground lightning strike. But what happens is it initiates from the ground toward the cloud. When we look at it, when we're looking at cloud-to-ground lightning with our own human eye, we only see the big bolt coming down from the cloud to the ground. It looks like it's going the other way. But in reality, these positive charges are flowing up the taller objects such as trees, and the potential or difference between the negative and positive charges on these taller objects on the Earth's surface, they're overcome to where it creates a lightning strike, a lightning bolt. And what happens is, what we really see is the large number of electrons, the negative charges at the base of the thunderstorm cloud, flowing to the ground, resulting in the more ominous return stroke. So this portion, as the positive charges move up taller objects, trying to meet the negative charge, opposite charges attract, right? Positive charges moving up this tall tree. This is going to initiate what's known as the stepped leader. That's what I'm talking about right here. Step leader, where was it at here? Right here. As the step leader approaches the ground, the potential gradient increases and a positive charge starts upward from the ground. Right? So we have a step leader effect here. And again, our eyes just see a lightning bolt from the ground, from the cloud to the ground, so we can't really decipher that difference. And sometimes there is more than one stroke, but more often the leader and stroke process is repeated in the same ionized channel at intervals of about 0.04 of a second. This is what makes it so difficult to get these cool lightning bolt pictures. The time exposure, it has to be really good, and also timing has to be on your side if you're a photographer, because it happens so quickly. 0.04 of a second is very fast. The subsequent leader, by the way, is known as a dart leader, and the dart leader is going to proceed from the cloud along the same ionized channel as the original step leader. And as that leader approaches the ground, a less energetic return stroke, then the first one travels from the ground to the cloud. A lightning flash will usually have 3 or 4 leaders followed by a return stroke. Here is some more diagrams to kind of show you the charge differences. Here is, it's funny too because there's a tree on this diagram. I was kind of trying to show you that. This is why they tell you never to stand near taller objects when lightning is occurring. You don't want to be near taller objects because the positive charge is basically going up the taller objects, and you're eventually going to have an ionized channel where you get a step leader coming down out of the cloud. The negative charges are beginning to meet up with the positive charges here on the tree. And then look, the bolt hits the tree. You don't want to be near that. And then you get a stroke leader. And see how there's multiple forks of lightning off the ionized channel? All right, so then to end today's training, I'm going to go into lightning types. We just talked about formation of lightning. Now let's talk about lightning types. There's something known as forked lightning. When a dart leader moves towards the ground, deviates from the original path taken by the step leader, the lightning is going to appear rather crooked or forked. There's ribbon lightning, which forms when the wind moves the ionized channel between each return stroke, causing the lightning to appear as a ribbon. That one's not as common. There's ball lightning, appears as a luminous sphere that floats in the air or slowly darts about for several seconds. And then there's sheet lightning, which is very common, sheet lightning. It forms when either the lightning flash occurs inside a cloud or intervening clouds obscure the flash. They appear as a luminous white sheet. So sheet lightning is a very common type of lightning that we see with thunderstorms right there. Heat lightning, now, it's funny because I was asked this a while ago. Is heat lightning really something that exists? And the answer is yes. And I've seen heat lightning in the Midwest, actually, where you have a large area of flat land in the Midwest. It's not really hilly or anything like that. And so you can see like flashes of lightning quite a distance away from distant thunderstorms. But the thing is that lightning is so far away that you cannot hear the thunder yet. It's just too far off in the distance. And then we call this heat lightning in the summertime, where you get distant lightning from thunderstorms that's seen, but again, thunder is not heard. It's too far away. Frequently occurs on hot summer nights when the overhead sky is clear. Yeah, you'll look straight up and the sky's absolutely clear, but you'll see occasional flashes of lightning in the distance on the horizon, and you won't hear thunder. So we call that heat lightning. All right, that pretty much wraps up today's training, 12B, how the weather works. Talked more about thunderstorms. Covered a lot today. A lot of interesting features with thunderstorms. We started off with gust fronts, which act similar to cold fronts. Much cooler air behind gust fronts, and that cooler air is meeting the warmer, moist air out ahead of it. Temperatures can drop rather abruptly when you have a gust front. Additionally, we talked about special types of clouds, shelf clouds, as well as roll clouds, and kind of talked a little bit, showed you what these look like. Shelf cloud here upper left and roll cloud on the bottom. Talked about outflow boundaries, downbursts, and microbursts. Types of downbursts are macro and microbursts. The size matters. And showed you some examples on Doppler radar reflectivity products of an outflow boundary. By the way, the outflow boundary, I forgot to mention this, is an area of weaker reflectivity, by the way. Talked about here's some visual depictions of downbursts and microbursts and macrobursts. Again, talked about a special type of thunderstorm cluster known as a derecho, as well as a distinctive feature, specifically with squall lines, that's known as a bow echo. Kind of showed you what these look like on radar reflectivity, derechos, upper left. What kind of damage they can do, bottom left. And then talked about bow echoes. Additionally, we talked about mesoscale convective systems. We delved into squall lines. We talked about MCCs. We also talked about where thunderstorms typically form in the United States, the highest frequency, thunderstorm days, lightning and thunder, how lightning forms, how you can calculate the distance of a lightning strike to your location by using the 5 second for every mile rule. So you see lightning, count the number of seconds. For every 5 seconds, that's another mile away from the lightning strike. Lightning climatology, just kind of showing you where around the world lightning tends to be occurring at the greatest amount. Electrification within the clouds, how lightning forms, the electrostatic differences within the cloud, formation of lightning in general, and then talked about step leader, dart leaders, as well as the different types of lightning. Okay. All right, that wraps things up today. It's been a little bit of a break for me. I can't believe it's already been 2 weeks since the last video. But anyway, we're back, and we're going to continue to move on with the training series, How the Weather Works, as well as that meteorological history series. I still have Carl Gustav Rosby to talk about, as well as Theodore Fujita, Mr. Tornado. Those are videos that we'll be following shortly. Additionally, my next topic, I plan to do a video on tornadoes, which is always real interesting, including tornado resources. So looking forward to that. All right, that wraps things up. Thank you so much for subscribing to the Spot on Weather YouTube channel. Until next time, everybody, stay cool out there. It is summer. It is hot. It is humid in some places. Stay cool. And until next time, take care and God bless everyone.